Problem 40 states, a 50 kilogram sprinter starting from rest runs 50 meters in 7.0 seconds at constant acceleration. For A, they want to know what is the magnitude of the horizontal force acting on the sprinter, and for part B, they want to know what is the sprinter's power output at 2 seconds, 4 seconds, and 6 seconds. So I started out by listing all the variables given to us. We have our mass at 50 kilograms, our initial position at 0 meters, our final position at 50 meters, and our change in time is going to be 7 seconds. And I've drawn out our little sprinter guy on an axis here. Same, we've got 0 meters starting, 50 meters final. He's moving in the right direction, so drawing out a force diagram here, we have our static friction going to the right, which is going to be the only force acting on him in the horizontal direction. We have our normal force and force of gravity, of course, but those are in the vertical direction, so we're not worried about those for this problem. So to solve for force, we can use Newton's second law, and we know force equals the mass times acceleration. So here we just need to solve for the acceleration, which we can do using this equation here. We've got all our variables other than this acceleration. So we can just plug in our starting position, or final position, our starting position, and we know our initial velocity is 0 because we started at rest. So this whole part of the equation here we actually don't need to worry about because that'll equal 0. And then we have half of a equals our 7 seconds squared. So doing that math, we get our acceleration equal to 2.04 meters per second squared. And we can now plug that back in. Force equals mass times acceleration. And we end up with our force in the horizontal direction at 102 newtons. And now we want to solve for his power output at 2, 4, and 6 seconds. So for power, we're going to use the equation P equals the force times the velocity. So this time we're just going to need to solve for velocity, which since we already have the acceleration, we can use this equation here. We know our initial velocity is 0, like we set up here, because we started at rest. So we're actually just going to be plugging in acceleration times the time for each one of these. So same acceleration, constant acceleration. First, we're going to plug in our 2 seconds. We get 4.08 meters per second. We plug that into our power equation, and using that 102 newtons for force, we get 416 watts for his power output at 2 seconds. His power output at 4 seconds is going to be equal to 832 watts. Using that same equation, just plug in 4. And same thing for 6. His power output is going to be 1,249 watts. And this problem reinforces our learning goals for this week, which introduce the concept of power. And we're ultimately just using system-based thinking to develop energy models. Specifically, what is energy, how is it transformed, and how is it transferred, which we can see from our power equation here, how that energy is transferred.